Hello chemistry warriors. Today in this video we are on module 14 talking about kinetics, and we're going to go over pages 492 to 501 in your book, and we'll be including on your own 14.1 and 14.2. So this module kicks off with a close look at the hydrogen peroxide reaction, where it's decomposed into water and oxygen gas. So this is the formula for hydrogen peroxide, H2O2. And since we know that the delta G for this reaction is negative, it's less than 0, then we can conclude that it is spontaneous. So the questions for many generations have been, then why does it not completely decompose while sitting on the shelf? In other words, why wouldn't this reaction just continually decompose it so that in a short period of time? So some of the considerations when we answer that are, first of all, that obviously we've already considered what the delta G would be, the thermodynamic criteria. It would fit that criteria to happen at room temperature. However, the second consideration we have is how fast the reaction goes, the rate of the reaction. So perhaps if the reaction is just so very, very slow, it happens over years, then you're still likely to find hydrogen peroxide in the container even after a long time. So in the chapter, we move on to look specifically at how we can quantitate the reaction kinetics. And specifically, we'll define the reaction rate as the rate of change of a product in a chemical reaction. And that is abbreviated with the R being the rate, and that's shown down here. And the delta T here is the lowercase t, not the uppercase t, which would be temperature, but it's the change in time, right, is the delta T. And delta, as you remember, means change. So our rate of the reaction is reflecting the change in the amount of product in the reaction over the amount of time. The change in time, and it equals negative change in the amount of reactant and change in time. So one of our first looks at this would be at experiment 14.1 that's outlined in the book. We're not doing it, but we're going to look at how we would set it up and what the probable results would be. So in this reaction, we set up 4 test tubes, and so I have them numbered here. And we're in each one of the test tubes, we'll be adding some toilet bowl cleaner, some antacid powder or tablet, and perhaps in one there's some water to dilute. So for test tube 1, it's half a full with the toilet bowl cleaner with a portion of an antacid tablet. In the second one, it's the same amount of toilet bowl cleaner with the antacid, same type of tablet but crushed into a powder. And then third, we have the cleaner plus the tablet, which is the same as 1, but in this case we're going to heat up the reaction. And then number 4, we have a diluted version of the toilet bowl cleaner, and we add the tablet. And then in this column here, or row, we're looking at what would typically happen with these reactions. So in 1, you'd predict have some left, 2, probably all would be gone, 3, all would be gone, and 4, you'd have some left. And the variables that are set up for this reaction are variables that are known to affect chemical reactions, and those are the surface area, because we're looking at a tablet form of the antacid versus a powder. So when you're comparing these two with the surface area, you would expect this reaction to be more complete than this one because of the access of the antacid to the toilet bowl cleaner. Then our second variable would be the temperature. So we'd be comparing 1 versus 3. They have the same amount of toilet bowl cleaner. They both have a tablet, but this one is heated, so it would be typically reach completion sooner. And then finally, we have the concentration of the toilet bowl cleaner. The antacid stays the same in all in terms of concentration, but in this reaction, you're only adding a portion of the toilet bowl cleaner you did in this. So you'd be expecting some to be left in this because you just don't have as much of one of the reactants in it. So once again, our variables here are surface area, powder versus tablet, temperature, room temp versus heated, and concentration. So the chapter moves along and points out some important conclusions on these factors on chemical reactions. So our conclusions on temperature are outlined as such. To react, chemicals must collide with one another so that their electrons can be either transferred or rearranged. And we also know, so this is just sort of a model of that, imagining the electron transfer. And then also, higher temperature increases chemical reaction because the reactant molecules or atoms move faster, increasing the chance for a collision. So at cold temperatures, the molecules are not moving as quickly as at higher temperatures, and then this would increase the likelihood of collisions and therefore chemical reactions. Then we have conclusions on concentration here. Decreasing concentration decreases the chemical reaction rate because there are fewer reactant molecules or atoms to collide with one another. So in a concentrated solution, which would be on this left end, you can see the atoms or molecules have close proximity to each other, versus a less concentrated area, they're farther apart, so they'd be less likely to react. And then finally, increasing the surface area of a reactant increases the reaction rate because the molecules or atoms can mingle more easily with the molecules or atoms of the other reactants. So you could see here, like in the case of that antacid tablet, if you have a whole entire tablet, the surface area of this one bit of bulk material is less than what it would be if you have the particles in very, very small pieces. Okay, so let's look at on your own 14.1. Two containers are filled with the same mass of both nitrogen and hydrogen gas. If the first container is significantly larger than the second, in which container will the reaction be fastest? So our conclusion here is because the concentration of molecules is denser in the smaller container, that would be the one where the reaction would proceed faster. All right, let's look at 14.2. The muscles in an animal's body are run by chemical reactions. When these reactions occur, they contract the muscle, making it move. A biologist is studying a lizard and notices that when the lizard is in a cold place, it moves very slowly, but when it is in a warm place, it moves very quickly. Explain this observation in terms of chemical kinetics. So this situation is applicable to a lizard because it's ectothermic, meaning that it's cold-blooded. Therefore, its internal temperatures are affected by the ambient temperatures around it. So, in other words, when it's cold outside, the core temperature of this lizard would be low, and when it's hot outside, the lizard absorbs some of the heat, and then its core temperature is hotter. So when it's hotter, obviously then the chemical reactions that depend on temperature would proceed at a faster rate, and thus allow the lizard to move very quickly. And then the book points out too that this is not typically the case in mammals, because we're quote-unquote warm-blooded, and so our internal temperature is regulated and should typically be the same regardless of the ambient temperature. But obviously, people do get hypothermia and whatnot. There are situations that can affect our internal temperature as well. All right, so let's look at the rate equation. And in this model, it starts out with the capital letters A, B, C, and D. The A and B, these capital ones, are representing the reactants, and the capital C and D are representing the products. And the lowercase a, b, c, and d are representing the stoichiometric coefficients, so they'd be like the numbers before the elements. All right, so keeping this in mind, the capital A and the capital B are the reactants. They use those in this reaction equation, or rate equation. So the R is the rate of the chemical reaction, and the brackets, right, that are around the A and the B represent the concentration of whatever's inside of them. And those squarish type brackets are used often in chemistry, so you should remember that. That means the concentration of whatever's inside of them. Then our K is something new here. It's a rate constant for that particular chemical reaction, and it's unique for each reaction. And then our X and our Y are exponents for the concentrations of our reactants. So a little bit more on the rate equation. Okay, we can see that if A increases or B increases, right, then R will increase. So if we're increasing the concentration of either or both of these reactants, then it's going to increase the rate of it. And then the book also points out that the order of the reaction, sort of that concept, is the sum of the two exponents. So the X plus the Y gives us the overall order of the reaction. And so if we're going to apply this to sort of everyday examples, right, we have the rate of us doing our homework is equal to the constant times the amount of sleep that you have times the amount of healthy nutrients you have. As these increase, right, our rate of getting homework done increases. And then alternatively, if you're looking at the rate of binge watching, like your favorite TV series, that would depend on your access to your devices and the amount of snacks that you have in handy. All right, let's look at example 14.1. And again, just reminding you here of what the rate equation is. So it says, write the rate equation for the following chemical reaction. So we have N2, the nitrogen gas, and 3H2, the hydrogen gas, and forming NH3. And in this case, our A would be the N2, so I'll be putting our N2 in for the A. The H2 would be the B. And then for this particular equation, the book is satisfied with leaving it there. So the answer is just the R equals the rate constant, the K, of the concentration of the N2 times N to the X times the H2 to the Y. All right, and so now we're going to move on to another example that is going to involve some more calculations. And so you can get your calculators ready if you don't have them out. And we'll be solving for the rate constant K and those exponents X and Y. So let's look at this example. It says, a chemist runs an experiment designed to determine the rate equation for the following reaction. So we have the number 2 here, and then you have ICl. So it's I is iodine and the Cl is chlorine, so it's iodine monochloride, plus H2, which is hydrogen gas, okay? And then it's yielding the iodine plus 2HCl, the hydrochloric acid. So it says to do this, she runs the reaction 3 times, varying the concentration of the reactants. All right, so we know right offhand this is going to be our A, the ICl, and the H2 will be the B. And in our trials, right, we have some things that are staying the same for each trial and some things that are changing. So the changing would be like the variable in that particular reaction. So if we're just looking at trial 1 and 2, we notice that the iodine monochloride stays the same in concentration, but the hydrogen gas is increasing by 2-fold, it's doubling, and then our reaction rate is changing. So in order to just look at our y for this, which would be the exponent that is correlated with the hydrogen gas, we're going to just look at trial 1 and 2 in this next slide. So this is all about finding the y, because remember this B is the H2, and we're just trying to find the exponent that would correlate to that. So again, y is the exponent for the concentration of hydrogen gas, and we're only comparing the data between trial 1 and 2 because the H2 is doubled here, but the ICl stays the same. So this is our constant, this is the variable. So again, the ICl here stays the same, 0.25 molar. The H2 is 0.25 and 0.5, so that's doubled. And then our rate is in molarity per second, so it goes from 0.0102 to 0.0204. So what we see is this relationship here. The H2 is doubled and the rate is doubled. Since they're both increasing by 2, it's considered a 1-to-1 ratio, and it's considered a linear relationship. Imagine like a slope, if you had a slope going up this way. So in this case, our y is equal to 1. All right, now we're going to look at finding x. X, as you remember, is the exponent of the A, and in this case our A is the ICl. So x is the exponent for the concentration of ICl. And in this case we're comparing the data between trial 2 and 3 because the ICl is doubled, but in this case the H2 stays the same. So again, H2 is constant, ICl is doubled, and then we look at the rate change. Now in this case, the ICl is doubled and the rate doubles again here. So it's the same type of relationship we saw in Y. Since they both increase by 2, it's considered a 1-to-1 ratio. It's a linear relationship, so the x is 1. And so I'll just point out that when we finally plug in the value for x and y, which is just 1 and 1, they don't actually write a 1 there. It's just understood that it's 1 even though you don't write it. Okay, so now we have that rate equation. You have R equals the K times the concentration of the ICl times the concentration of the H2. We basically just plugged those in, the ICl and the H2 in here, and then we know that they're both 1. Now we can solve for K because we take the data and from trial 1 and plug it into this formula. So in trial 1, the concentration of both of these was 0.25 molar, so we put those in for A and B. We're solving for K, and the data gave us that the R here was this number, 0.0102 moles per second. All right, so then we just rearrange things and solve for K, and now we have our rate constant for that reaction. So that's definitely solving 99% of it. The book just goes on then to point out that if you wanted to imagine doing another trial, then you can take your rate constant and put it in for this K value, because it would be consistent for other concentrations. And then you can imagine, right, that you're plugging in sorry that's a little dark on the end, but imagine that you're plugging in 1 molar, right, for your A, for the ICL, and 0.75 for the B. You know that the exponents are still 1. You can put this number you got in for K here, and so you can calculate the rate for this sort of imaginary trial that you've done. Okay, on the next video we'll pick it up from there.